Hello everyone, my name is Tom Verstraten. I'm a professor at the University of Brussels at the Robotics and Multibody Mechanics Research Group. And today I will be presenting my talk, Compact Gearboxes and Innovative Actuators for Modern Robotics. And I'd like to start this presentation with a small explanation of why exactly we need new actuators for robotics. In recent years, an increasing number of robots have appeared which are battery-powered and perform highly dynamic motions. These robots place challenging demands on their actuators, which need to be highly backdrivable, they need to have high torque density, and they need to be energy efficient to ensure sufficient autonomy. Now, these requirements are often best met with electrical motors. However, in many cases, electrical motors do not provide sufficient output torque for the given application, which is why they are often coupled with a gearbox. Now, there is some design freedom there. The higher the gear ratio, the lower the output torque required from the motor. And so, what we really have is a design spectrum. And the range goes from direct drive, which is basically a high torque motor which produces enough torque to eliminate the needs for a gearbox. And on the other hand, we have electric motors coupled with high ratio gearboxes. We're talking about typical range which is up to 300 to 1. Now, since direct drive solutions are often technically infeasible, quasi-direct drive has emerged as an intermediate solution, where high torque motors are coupled to low ratio gearboxes. And here we're talking typically about gear ratios from approximately 20 to 1. And this brings us to the topic of this workshop. Should we go for direct drive solutions, or more generally speaking, drivetrains which incorporate high torque motors? Or should we opt for high ratio gearboxes? Now, before I move on to the technical solutions that we've developed in our research group, I'd like to start this presentation with an overview of what, in my opinion, are the pros and cons of high ratio gearboxes with respect to high torque motors. Let's start with the disadvantages of high ratio gearboxes. First of all, gearboxes introduce nonlinearity, such as friction and backlash. This makes torque prediction from the motor current very difficult, if not impossible. And this is something which is, of course, desirable because it facilitates force control. Similar story for backlash. In that case, if we want accurate position control, we might need a secondary encoder at the output to see the difference between input and output position. So overall, gearboxes might cause needs for more sensors in the drivetrain. Another obvious disadvantage of gearboxes is that they introduce high energy losses. This is especially the case for high ratio gearboxes. For example, the energy efficiency of planetary gearboxes is related to the number of stages of which they consist. And then, of course, there is also the higher acoustic noise generated by gearboxes. And gearboxes are typically the main source of this type of noise, more so than electric motors, which are relatively silent. They also exhibit large amounts of wear, more wear than the electrical motors again. And so there is an increased need for maintenance when a gearbox is introduced into the drivetrain. And then finally, gearboxes also introduce compliance, which could cause resonance problems. This is not an issue for direct drive motors, where the loads are coupled to the motor on a large diameter, which of course increases the entire stiffness of the coupling and effectively eliminates resonance problems entirely in these types of servo systems. But actuation systems with high ratio gearboxes also have certain advantages. Or perhaps it's better to say that actuation systems with high torque motors have certain disadvantages that can only be overcome with high ratio gearboxes. The main disadvantage of high torque motors is the fact that they draw higher currents, and this causes all kinds of problems. The first problem is a problem of commercial availability. The motor drives that are supposed to supply the current to the high torque motor are typically designed for smaller brushless DC motors of a more regular type. And so their current is also often limited to what is expected to be normal for these conventional motors. I have to add there that suppliers are gradually increasing those current limits in response to the increased interest in high torque motors. Another disadvantage are high joule losses, which are incurred by those high torque motors. This is really a combination of the high currents that they draw and the increased resistance that their windings have. And this is especially problematic when these motors are holding a static load, in which case the losses, the joule losses, would simply accumulate. Now, if we have a regular DC motor with lower joule losses and with a gearbox, possibly a high ratio gearboxes, these static loads can be held without any additional energetic losses at a relatively energetically cheap cost. Another disadvantage, which is also closely related to the higher currents, is that high torque motors may have problems with thermal heating. This is mostly due to the difficulty in evacuating heat generated through the energy losses, joule losses, due to the larger diameters of these high torque motors. This is especially a problem for outrunner motors, which have their winding placed inside and magnets outside, as opposed to inrunner motors. And this means that the convective airflow, which cools the motor, does not reach the windings where the heat is generated directly in outrunners. And this causes them, of course, to heat up more than they otherwise would. This then increases the winding resistance, of course, which is proportional to temperature, and consequently the joule losses, which in turn leads to further increased heating, and so on. So what we really have here is a cascade effect which is going on. Now, besides all the current and heating problems, high ratio gearboxes actually have some advantages when it comes to accurate position control. First of all, they amplify the encoder resolution, which is desirable. They reduce the influence of cogging torque, and overall they actually cause an increase in actuator impedance, which makes the drivetrain more robust to external disturbances. And then finally, a high-speed motor with a gearbox, possibly a high-ratio gearbox, is generally less expensive than a direct drive solution, or certainly a quasi-direct drive solution where you still need that additional gearbox. And so in many applications where cost is of importance, and of course we all know that there are many such applications, the conventional solution might be the more desirable one. Now, while it was certainly useful to get an overview of the pros and cons of the different solutions, we really didn't get to the heart of the problem. The main reason why high torque motors, or to put it in a different way, direct drive or quasi-direct drive solutions are being considered right now, is because they would offer better dynamics. And this is important for certain complex tasks or complex applications in robotics, such as legged robots and active prosthetics and exoskeletons. Now, there are really two sides to the problem of dynamic performance for actuators. One is the efficiency perspective, which is something that we briefly talked about in previous slides, and well, we already saw that it's really a complicated matter. But the second side to it is an inertia perspective. We're going to look at how the inertia of the motor and gearbox are being reflected to the load. And this is what proponents of direct drive and quasi-direct drive solutions typically state as the main motivation for their choice. Of course, if we're going to use a high ratio gearbox, the I square term is going to blow up the I square factor is going to blow up the first term of the motor inertia, and so that one's going to become dominant, and we're going to have an actuator which is less performant overall. There is, however, one thing which we do need to consider, and that is the fact that high torque motors also tend to have higher inertias. This is due to their larger diameter. These are, of course, opposing effects, and so we have to ask ourselves the question, which one of those effects is going to be dominant? Now, an attempt to answer this question is the derivation of so-called scaling laws. These scaling laws show how certain performance metrics, like torque or drivetrain's inertia, evolve as a function of parameters of the design of the drivetrain. Now, my research group has a number of publications on such scaling laws derived for typical actuators in robotics. You can see a list of publications right here. Now, I'd like to focus on one specific paper, the 2019 paper on scaling laws for robotic transmissions. While I was going through this paper, I found an interesting graph that we set up, which is related to this problem, and it depicts the torque generated by different types of motors and gearboxes, their torque as a function of the inertia. I won't go into detail about the interpretation of this graph. It will take me a few minutes to explain it properly, but the main result from this graph was that for the Maxon motors that were characterized by this graph, we were limited to one specific manufacturer. For these motors, it appears that if we select a flat motor, so a high torque motor from this brand, and we design it for a specific application, we will end up with a drivetrain which has a reflected inertia to the loads, an effective inertia, which is similar than the one that we would find if we were to design a drivetrain consisting of one of their classic or typical brushless DC motors with a regular gearbox. In this specific case, we can also graphically see that the geared brushless DC motor of the cylindrical type, so the conventional type, would have or would generate a lower effective inertia for the entire drivetrain up until a gear ratio of approximately 100. That is already quite high, as you can see. Now, I won't go into detail about how I did this analysis, but for more explanations, you can check out a video on my YouTube channel, which you can access by scanning the QR code on this slide. Now, in recent years, a growing number of researchers has started claiming that direct drive and quasi-direct drive solutions are really superior to the conventional geared brushless DC motor solutions. Now, I would like to say that it's really not that obvious. The claims that have been made in the past for those high torque motors have mostly been based on intuition or on practical experience, but up until now there's really no real proof to say that this is the case. Now, of course, there have been some analyses done that supposedly prove that high torque motors are indeed desirable, but many of these analyses don't really take into account several important constraints of the technology, especially the thermal constraints that, as we have seen earlier, really play an important role for these types of drivetrains. Scaling laws can be one way of moving on to, let's say, proof for the high torque case or the high ratio gearboxes case. But these scaling laws are also often limited in the sense that they typically describe the trends in the technology, but not the full function that gives the relationship between, again, those performance metrics and the actual design of the motors or the gearboxes. Moreover, those parameters are often very complex and multidimensional and therefore very difficult to represent. So that's another challenge when it comes to scaling laws. So it seems, from my point of view, that right now comparisons using data from manufacturers, like we did in the previous slides, are really the only way to evaluate whether one solution is better than the other. And I do expect that in future years we will see more of these analyses and perhaps case studies explaining the choice for one over the other. Now, I have to say that the analysis that we presented in the previous slide does have some shortcomings, or let's say that was very basic and neglected several important aspects. For example, efficiency. We didn't talk about efficiency, but it also plays a very important role in the comparison, of course. And although, well, as mentioned previously, both direct drive solutions and gearboxes have some disadvantages when it comes to efficiency and have some problems there, it does appear that direct drive or even quasi-direct drive solutions would be slightly more energy efficient. And that would also mean that, going back to the comparison of the previous slides, that the final outcome might be slightly more in favor of direct drive or quasi-direct drive. That's one very important point. And a second very important point that I would like to add to the previous slide is that due to evolutions in technology, and here I'm talking about both motor and gearbox technology, the lines in the graph could also start shifting over the coming years. And in fact, I do believe that they will. And so this is one aspect that I would like to focus on in the next slides, because at the VUB, we have been working on improving gearbox designs. This is the work that I would like to present in the coming slides. Typical gearbox technologies that are being used in robotics are harmonic drives, cycloid gears, and planetary gears. You can find an overview of the pros and cons of these gearbox technologies in our review paper that we recently published last year in Frontiers and Robotics and AI. The reference is at the bottom of the slide. Now, all these technologies, gearbox technologies, have certain advantages and disadvantages. We made a very simplistic representation on this graph. Of course, it strongly depends on the size of the gearbox. For example, in the case of planetary gears, it depends on the number of stages. And of course, this simple graph cannot fully represent the scope of the technology. What we can say, however, is that all of these technologies require drastic improvements for them to be really, let's say, capable of outperforming the direct drive and quasi-direct drive solutions that we've talked about in the previous slides. There is especially a problem when gearboxes are required to have a high reduction ratio or gear reduction. In that case, efficiency often drops very drastically, and also in terms of weight, these gearboxes fail to perform very well. Now, we think that at VUB we have found a great solution to this problem, and this is what is called the Wolfram gearbox. Wolfram gearboxes are particularly suited to generate high gear ratios, and at the same time it can also perform well in the other performance categories, provided of course that it is properly designed. The trick behind the Wolfram gearbox is to use compound planetary gears. You can really see those as two planetary gears which are rigidly attached to one another with the same axis of rotation. Now, if the number of teeth on those compound planetary gears is similar, one can easily create high gear ratios, which can reach in the orders of hundreds to one. Now, this idea is certainly not new. The Wolfram gearbox itself, for example, was invented already in 1912 by Urs Wolfram. The reason why it didn't really catch on is because there are some issues related to efficiency in this type of gearbox. By the way, I will add that similar efficiency issues are also present in the technologies that we've seen before and are really shared by any high ratio gearbox. Now, we've investigated the fundamentals behind the efficiency problem, and we came up with a solution, a novel Wolfram gearbox, which is patent pending, by the way, which solves these issues. And the key innovative step here is to split the first stage of the gearbox, which allows us to optimize the meshing of the gear teeth in such a way that it can be more energy efficient and that the bending and Hertzian stresses are better balanced in a specific gear tooth. Our team has built a number of proof of concepts which all share high reduction ratios, typically between 100 and 300 to 1, and which can deliver torques of around 100 Newton meters. This is to make them suitable for application in powered prostheses and exoskeletons, which is one of the main research topics of our research group. Some of these prototypes have already shown very promising results in terms of efficiency and backdrivability, in particular the proof of concept shown to the right. We are currently still in the process of testing these prototypes on our back-to-back test bench for energy efficiency, and you will no doubt see results of those tests in the near future in conferences and in journals. That's it for today. If you have any questions, feel free to send me an email or to connect to me on one of my social media accounts. I'd also like to remind you, as one of the organizers of this workshop, about our panel discussion, which will take place on the 27th of September, so that's on Monday, from 10 past 4 to 10 past 6. Hope to see you there, and enjoy the rest of your day. Bye.